Well, now it's on to Lecture 6, Detection of Signals and Noise. And here is our block diagram of the radar. Here's the section that we're going to be looking at, detection. I want to point out to you in the big picture that we're going to be looking at the detection of a single pulse of data. The detection process will work on a single pulse of data, and then we may add up different pulses to it. But the background we're dealing with is Gaussian noise. And that's one important type of processing in a very general sense, I mean that we're going to be doing. And we're going to be step by step through consecutive lectures throughout the course looking at a number of different techniques within the radar, some of which will have to do with the antenna and how we place nulls optimally in the antenna side lobe pattern, and others on how we do signal processing to reject backgrounds that aren't noise-like but are colored, that have a Doppler spectrum that's not uniform. And each of these different areas the three that I just mentioned, this one and in here, are going to have intrinsically the same kind of a process. What's the optimum way to optimize the signal relative to the background? And I'm going to point out at each time when we go through those successive steps how they all interrelate so that you can see in your mind the big picture, because in the last lecture, the next to the last lecture, 18, we're going to put them all together. Okay, now we're going to talk about detection of the signal so that we get thresholding and then the results, a target detection. First, we're going to talk about the basic concepts of probability of detection and false alarm and signal-to-noise ratio. There's got a lot of, you'll see a lot of graphs that connect those three terms, and they are lots of times called ROC curves or receiver operation curves. Then we're going to talk about how we add up pulses, the detections from different pulses. Then we're going to talk about what happens when the target is fluctuating. For these initial calculations, we'll look at the target as a constant, non-fluctuating object, like a sphere. And then we're going to look at how we set our thresholding adaptively so that we can have a constant false alarm rate through varying levels of noise. Then we'll summarize. Now, to put this in perspective of an actual radar, and so there's not just mathematical in terms, we're going to go back to our old friend, the airport surveillance radar. And it is a mechanical scanning radar which rotates at 12.7 revolutions per minute. And here is a picture of its antenna rotating. Here's the beam pattern. And here's its beam width. And within that beam width, it's at S-band. Within that beam width, there'll be a target that you want to see, or maybe there'll be no target. But there's going to be, in that beam width, a number of pulses will flash by the target. The transmit pulse rate is 1,250 pulses per second. And that means that in this beam width, as it goes by a target, there'll be about 20 pulses. And this radar can see out to about 60 miles, a small single-engine aircraft, and it's all, as I mentioned before, all major airports in the country. Now let's look at in detail at the range azimuth Doppler cells that are going to be thresholded. And for our typical airport surveillance radar in ASR 9. In a half beam width, there are about 10 pulses, and we're going to process them into 10 filters, 10 Doppler filters. So we're going to have input in the time domain, and we're going to have a set of weights that will, 10 different sets of weights that will multiply the complex returns, the in phase and the quadrature, the I and the Q, the real and the imaginary part, twice at 2 different pulse repetition rates to deal with a Doppler ambiguity problem, which I'll discuss. So we have 22 pulses per beam width. And so in one revolution of the radar, we have about, the range resolution is a 1/16 of a mile, so we'll have about 960, about 1,000 range cells. We'll have about 500 azimuth cells of 10 pulses. And we'll have about 10 Doppler cells. Some radars use 8, some 10. And that gives you 5 million range azimuth Doppler cells, approx order of magnitude, every 4.7 seconds, about 5 seconds. So that's an awful lot of decision making to do. Now, for each one of these cells, we want to ask the question, is a target present in each cell? Now, if we look at, as a function of range, in blue, the noise, and in red, the targets. There's one at about 65 miles and another at 125 miles. And this isn't for that 60-mile airport surveillance radar. It's for just a generic radar. What we do is we receive power back from the target, the echo that we receive, and some of it's noise, and some of it's due to targets. And we have to set a threshold, a level, where above that we declare it to be a target, and below that we declare it not to be a target. And we can have 4 different kinds of things that can happen. Now, the received background noise fluctuates up and down. It's a random variable. And for the targets at this point of discussion, the target echo also can fluctuate, but for our original discussions, we're going to consider just a constant target. But generally, the target can fluctuate. If a target is present at a given range, we need to set a threshold, some constant or variable threshold. Here we have a constant threshold. And the detection performance, the probability of detecting the target when the target is present, depends on the strength of the target relative to the strength of the noise and the threshold. That's the signal-to-noise ratio and the probability of false alarm. So the probability of detection is related to the signal-to-noise ratio and the probability of false alarm. What's the probability that the noise will be above a certain level? And here we have a strong target that's detected. It's above the threshold. Here we have a false alarm, which almost gets detected. And here we have a weak target, which is not detected. Excuse me, this false alarm, this blue dashed line, it should go up a little further and just barely be detected. That was a mistake in the artwork. Now, looking in terms of hypotheses at this radar detection problem, we have the radar receiver, we make a measurement X, and we do processing on it. And we have the 2 decisions, H0 or H1. The target absent hypothesis, H sub 0, means there's noise only. And the target present hypothesis is H1, and that is there's signal plus noise. So you do have a signal. So in this case, our measurement is N, the noise random variable, and X, the sum of these 2 random variables, and they have probability density functions. the probability density that with a measurement x, which we make it, will have this outcome or that outcome. Either there will be noise only or target. And for each measurement, there are four decisions. And on one axis, we'll put the decision, and on the other axis, we'll put what truth is. When there's noise present, and we say we don't think there's noise, we don't report it. When there's a target present, and we say yes, there is, that's a detection. But when we say there's a target present, but there isn't, the truth is not, that's called a false alarm. And then there are misdetections when we say there's no target there is our decision, just noise, but there is a target there. The probability of detection is the probability we choose H1, that there's a target present, when that is true. And the probability of false alarm is the probability we choose H1, that a target is present, when there's noise present. And the objective is the Neiman-Pearson criterion that we want to, when we do our mathematics, we want to maximize the probability of detection subject that the probability of false alarm is no greater than a specified amount. The probability of false alarm is less than or equal to alpha. And here is that likelihood ratio test. Now, let's first look at just the noise density, the probability density of noise, of Gaussian noise, as a function of the voltage. Here it is. Here's the probability density. Because it's a probability density, if we integrate over the whole curve, we'll get 1. And we set a detection threshold here, a little above 2 volts. So noise is only, no targets are present. The targets are absent. Now the probability of false alarm is the integral of this noise probability density from the threshold up to infinity. It's the probability that the threshold exceeded a given target absent, i.e. the chance that noise caused the false alarm. And we want this probability of false alarm to be very, very low, as low as possible. Now, if we have a target present and noise present, there is a separate distribution for the probability density that we get. And that's this density in the red. It's the probability of our measurement when there is a target present. And here we have the integral under this curve is the probability of false alarm. Now, the integral from that same threshold up to infinity of this distribution is the probability of detection. In what is pink, that's including this area underneath here. That's the probability of detection that the threshold exceeded, given that a target was present. Now, this is an example with different signal-to-noise ratio. We've compressed down and spread out the voltage. And here we have a probability of false alarm of 10 to the minus 1 is set. So this is 1/100th of the area of the whole curve. Now, for a signal-to-noise ratio, the ratio of the signal plus noise to the noise is a factor of 10 dB. If we integrate from that point up to infinity, we get 0.61. If the signal-to-noise ratio were 20 dB, the integral under the curve goes effectively very, very close to 1. So that you can see that 10 dB makes a very big difference. So PD, the probability of detection, increases with target signal-to-noise ratio for a fixed threshold. Notice this threshold has been fixed. And raising the threshold reduces the false alarm probability, the false alarm rate, and it increases the signal-to-noise required for a specific probability of detection. So if we raise this up, it increases the signal-to-noise ratio that required for a really solid probability of detection. Now for non-fluctuating targets, this is the algebra that one goes through. Now this work was first done in 1954 by Markham. We're summarizing in a view graph what he did. It was about 60 pages when I read it back in the 70s. The Rayleigh distribution is the noise voltage, and the distribution of signal plus noise, its probability density function is Riceian, and this is an expression for it, and the signal to noise ratio is just R over 2 in these units. We set the threshold R sub t based on the desired probability of false alarm, and if put in whatever false alarm you want, work your way back through. Note this is a logarithm to the base e, and it will tell you where to put your threshold R sub t. And so you can compute the detection probability for a given signal to noise ratio and false alarm probability, which is just this integral, which is the Markham's Q function. And this Q function is this integral, which is calculated numerically from where you notice A and B are the square root of twice the signal to noise ratio and the square root of minus 2 logarithm to the base e of PFA. You plug them in and you'll get the relationship, the probability of detection, and you'll have plugged it in for a PFA and for a given signal to noise ratio. And you can see, since there are 3 distinct variables of interest on a two-dimensional plot, we're going to have a family of two-dimensional curves. And this is what those two-dimensional curves look like for a steady target. Here, the probability of detection is noted on the y-axis in linear units. You're going to see we're going to be going to another set of units in a minute that squish things down. Because you can see, it's hard to read off what's a 0.99 and a 0.98 up here. And it's for a series, the probability of detection versus signal-to-noise ratio, and that's in dB, as a function of different probabilities of false alarm. Now, this is one good thing to remember, that, and it's like a rule of thumb. A radar will work well if it's got a steady target and you've got a probability of detection of 90%, 0.9, and a probability of false alarm of 10 to the minus 6. That's a probability of false alarm per decision or per cell. And remember, in that airport surveillance radar, we had millions of cells. So what you want, a few tens or 100 or so or whatever of false alarms per scan over this whole giant area. You've got to have a very small probability of false alarm because you're making that decision many, 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 many times, millions of times. And for higher resolution radars, they'll be going up into the 10 to the 8th. and you need 13.2 dB. That's something that I've had in my head, pi is 3.14159.2653.5897. You know, it's, a professor once said to me that those kinds of things are, if you remember them, you're either brilliant or you're stupid. And the reason is that you remember those things, you're either a genius or you fill your mind with trash. Well, just through using this over and over again, I remember this one, probably the pi is trash, you know. So what we remember, it's one thing radar engineers remember. About 13.2 dB, you get 0.9 probability detection and a probability of false alarm of 10 to the minus 6. And that's with a target which does not fluctuate in amplitude. The model of that would be a sphere. Okay. Now when we go to an axis that's distorted so that we can read very easily small numbers and large numbers, these numbers, the curves become much more linear. But they're the same curves. But remember, we said we want the probabilities of detection to be very, very high, and to be able to measure them off of a curve, you want to be able to read these numbers accurately. So this type of a curve is what's usually published in a book.